Hello, it's Stat 135, Lecture 39. Homework 11 will be due on Monday at 10 p.m. The schedule for this week is Bayesian statistics today and Friday. On Friday in lab you will review. For our week, Monday and Wednesday, they'll be in-class review with me, and I'll also be having office hours on Monday and Wednesday. Friday, there won't be any lab, but instead Friday, there'll be an in-class review with the GSIs. Today, we're going to talk about the Bayesian approach to parameter estimation. So just a quick probability review, Bayes' rule for x and y with joint density. So the conditional density is the ratio of the joint over the marginal, and a picture is shown here. So you can imagine the joint as being a surface over the xy plane, and the conditional density is a slice shown in orange here for of that joint. So we can write fy given x as fx given y times fy over fx. And in applications that we'll be doing, the conditional density is used as both the posterior and the likelihood density, and the marginal fy is used as the prior, with the denominator just being a constant. Also recall the beta distribution. X is beta rs, has the following density. Note the variable part, x to the r minus 1, 1 minus x to the s minus 1. Also remember that the expectation of beta is r over r plus s. So the frequentist approach to parameter estimation treats your parameter theta as a fixed constant known only to Tyche. You're given some data, you form a joint density called the likelihood density, of which you can use to, say, maximize and find the MLE, or you can find the MOM estimate by using a technique shown during the course. These are random variables, and you can calculate the SE and the CI analytically or by bootstrapping. Under the Bayesian approach, we treat theta as a random variable with density f theta, called the prior density, that describes prior knowledge about the distribution before you observe data. Then we observe data x, and we refine our knowledge about theta. So how does that work? So we compute the posterior density, and we employ Bayes' rules. So the posterior is the likelihood times the prior over a constant. In what we really care about is, we don't care about the constant, we care about the variable part. So it's best to say that the posterior is proportional to the likelihood times the prior. Typically, the posterior will be narrower or a sharper distribution than the prior, meaning once you've seen data, you've decreased uncertainty about what the true value is, or what the most likely value of your parameter is. So as an estimate of theta, we take the mean of the posterior. So we call that the posterior mean. So the expectation of theta given x. For a particular x, it is a number. So theta hat is the posterior mean is a random variable. It's a function of x. Taking the expectation of the posterior mean by the property of iterated expectation gives you the expectation of theta, which is as close to saying that theta hat is an unbiased estimate of the expectation of theta. You flip a coin 20 times and get 13 heads. Do you have a fair coin? Well, the frequentist approach would be to compute an ML estimator, which is 0.65. The Bayesian approach would be to say, okay, I don't know anything about this coin, so my prior is just going to be flat. It's going to be uniform 0, 1. X is the number of heads in 20 coin tosses, so my likelihood is binomial 20p, which has the following likelihood density, or probability mass function. And so my posterior is proportional to the likelihood times prior. So it's proportional to p to the 13, 1 minus p to the 7, which I recognize as beta, in particular beta 14.8. So then my posterior mean would be the expectation of a beta 14.8, which is 14 over 22. In other words, 0.63. So here I've drawn for you the beta 14.8 distribution, as well as the beta 1,1 or uniform 0,1 distribution, which was our prior. And you can see that indeed the posterior is more pointed than the prior, as that we have now collected data. So before we would have estimated our p to be a half, and now that we got 13 heads, we shift it to the right. So we can repeat the experiment, getting x is 8 heads. Now the prior is beta. We're going to make the prior our old posterior, and we get a new density, a new posterior. So to calculate that, the posterior is going to be the likelihood times the prior, proportional to likelihood times the prior. I just care about the variable part. The variable part of the likelihood is p to the 8, 1 minus p to the 12th, and the variable part of the prior is p to the 13, 1 minus p to the 7. So we get p to the 21, 1 minus p to the 19. So the posterior is a beta 2220, or the posterior mean is now 22 over 42, or 0.52. Now, when the prior and the posterior distribution belong to the same family, we say that the prior and the likelihood are conjugate. So the likelihood is playing nice in the sense that the posterior is having the same, it's allowing the posterior to have the same form as the prior, or the same distribution. So for example, if the prior is beta, then the likelihood could be binomial or geometric. So then we would have conjugate pairs. As another example, more general, if p is beta rs and x given p is binomial np, so we showed that p given x is a beta r x plus r n minus x plus s. So here's another example. If you have data x1 to xn that's Poisson, and the likelihood is, so the likelihood here, I've written out the probability mass function, and our prior is going to be gamma, say gamma alpha lambda, and I've written out that density, and I've also reminded you what the expectation of a gamma is. So I asked you guys to find the posterior distribution of theta given x, find the posterior mean, what is the posterior mean for large n, and is theta and x given theta conjugate pairs. So we compute the likelihood, and then the posterior is the variable is proportional to the variable part of the likelihood times the variable part of the gamma prior, and we see that that is indeed a gamma. In particular, it's a gamma sum of the xi plus alpha lambda plus n. Now, then the posterior mean will be the sum of the xi plus alpha over lambda plus n, because the expectation of a gamma is just the ratio of the two parameters. So now as n goes to infinity, note that the sum of the xi will get large, so alpha will be insignificant, as will lambda be insignificant compared to n. So we get x bar, which is the ML estimate. So that's the way the posterior mean works, is asymptotically it's actually normal, or approximately normal, and converges to the ML estimator when regularity conditions are satisfied. So we see that the Poisson and likelihood, the Poisson for likelihood and the gamma for prior is a conjugate pair. Okay, so we'll talk about more theory about Bayesian statistics on Friday. Have a great day.